Okay, so as a company, we have our NDA is to do research. So we work a lot with universities. One of them, UPV, Polytechnic University of Valence. And from there, together we do some developments. They also do patents with different innovation fields. One of them, corrosion. But we work on different IoT sensors for infrastructure to monitor not only corrosion. We can monitor other topics like, for example, here is a list of our main 4 areas, the basic areas. One is MONSEC. It's a sensor that it's monitoring the concrete strength when you pour the concrete in a new building to make a new infrastructure. What we monitor is temperature, humidity, and compression resistance of concrete when it's during the pouring process. So until you get some maturity, what we perform is just wireless sensor or cable. It depends on the size of the concrete. If it's a very massive element, then we have some cabling because we need to go very deep. If it's surface, at 20, 30 centimeters of the surface, we can put wireless sensors. We spread the sensors around the platform, and then we start measuring already the concrete resistance of the. This is very, very positive, very effective in order to then to remove the formwork, to take decisions afterwards in order to have a time schedule, a very concrete time schedule, or from when can we already remove the concrete and start next steps with a very good precision, because this is a system that it's compatible with the probe system, that when you take specimens and you break the specimens, you get the resistance. So this is a wireless method that it's not intrusive, so we do not destroy any piece of the concrete. And also, MONSEC has a prediction method, so we include also algorithm to have prediction in the future. So Corrochip is the one that is based this presentation today. It's a sensor that basically to monitor the corrosion in rivers, in reinforced concrete. Trenchip, it's another sensor that, because our company started with knowledge also more on telecom sector, we developed several antennas. One of them that is used is a Trenchip because it propagates very well the signal underground. So you can go deep as 1 meter, you can put a passive antenna and you can detect this antenna. And we use it, in fact, to detect underground pipes, infrastructures. So from the top, when they are covered, you can digitalize these and you can detect and get all the information of what you have underground. You have water, fiber optics, electricity, pipes. So this kind of facilities, it's a way to detect them and to digitalize and to get all the information from these assets. And finally, Corrochip, it's another of the technologies that we develop, and it's a sensors to detect and when there is some falling rocks in slopes. So we detect the speed of the rock that is falling down. We detect where there is an extra effort in the mountain, where there is some possible collapse due to some strengths that suffers the mountain. And for that, what we do is in the slopes, in the fences, we provide several sensors, and there are some gateways that get connectivity to the network and then send some alarms and some things into the net. So this is at least the presentation from Witeklab. And I would like now to pass through Roman, that he will explain better about Corrochip.
Hi. Okay, let me share my screen. Okay, so my name is Roman Bataller. I'm an engineer at Witeklab. I was previously working in UPV, and I'm a part of the researchers that patented this corrosion system. I will make just a brief introduction about why the Corrochip system just came real. Corrosion, you're very familiar with the problematic. Just to make this small introduction, I wanted to share with you this famous diagram that was provided at the beginning of the 80s by the Swedish researcher Dr. Tutti, which proposes that the service life of reinforced concrete structures can be divided into main time periods. Okay, one initiation stage and propagation stage. Many interpretations of this diagram have been made since it was published about 40 years ago. I here show you a recent one that was published by Dr. Rodriguez in 2021. In general walls, I need to say that the first block on the left corresponds to the ingress of aggressive agents in the concrete onto the rebars, which are mainly CO2 and chlorides, which result in a progressive disruption of the passive layer on the steel surface. And then you can see that on the right, the propagation stage, which is the active stage of the corrosion until the degree of damage reaches the limit tolerated by building standards. Okay, so concrete is the second most used material in the world after water. So sustainable business culture in construction industry is reflected on the life cycle design for new infrastructure and lifetime extension of existing structures. For aging structures that are the ones that worries us the most, customized maintenance plans should be devised. Actually, deterioration of a component cannot be precisely estimated in advance. Thus, periodic inspection and monitoring programs are advised. Besides, revealing the actual asset's condition with this approach aims to reliably project the structure service life and to help decide if and how an effective life extension of the assets can be accomplished through maintenance measures. For this, we can identify three key actions for maintenance: prediction, prevention, and correction. The predictive is a maintenance strategy that aims to prevent failures and unplanned downtime. This is done by regularly perform maintenance work before something breaks down. For preventive maintenance, we can say that it's regular and routinely performed on assets to reduce the chances of failure and unplanned infrastructure closure. Effective preventive maintenance is planned and scheduled based on real-time data insights. And in the end, corrective maintenance is any task that corrects a problem with an asset, which can return it to its proper working order. You can see this diagram on the right of this slide. So you can see how corrections and works on the performance of a structure can enhance and expand its lifetime. Okay, we'll continue just focusing on monitoring strategies regarding the evaluation of parameters of interest in corrosion. We can identify the strategies based on manual periodic inspection and those based on remote monitoring. For manual, as you can see, they're usually undertaken once the corrosion is obvious, and it can be performed exclusively on elements which are access to the workers, and usually has high inspection costs related. Some of the manual on-site methods require destructive or semi-destructive measurement methods. For remote monitoring, they are usually based on continuous non-destructive tests, often by means of embedded sensors like the ones we will propose later. They can be performed on accessible and inaccessible areas, and they allow the early detection of pathologies. This is important that they are suitable for long-term monitoring, and in the end, these strategies can be adapted for already built assets, but sometimes after complex installation processes. So now here present Corrochip monitoring system, which is an innovative system for the detection and evaluation of corrosion rebars. This allows the identification of corrosion processes, and we can perform daily measurements on the structure to obtain useful information about how these processes evolve. As I said, it's based on the use of embedded sensors. Data is sent to a cloud server, and then the data we store them. It's processed with a later algorithm. From the output of these analyses, we obtain physicochemical parameters that can be consulted later via a web application. This data is obtained by this novel technique that's called pulse potential step voltammetry, which is based on the tuple extrapolation method that will be developed later by our colleague Jose Enrique. So the system is suitable for existing structures and of course for new structures. These sensors measure parameters such as corrosion currents, corrosion potential, corrosion rate, and some others. The interpretation of this information allows to anticipate severe corrosion processes, which might deteriorate the metallic reinforcements inside the concrete. This is a powerful tool for long-term monitoring, which will provide valuable information for the design of effective maintenance plans. Not only having a direct impact on economic savings, which related to the extensive repair procedures, but also enhancing safety in the use of such concrete assets. So this is two examples. Well, I will show you a few examples on installation of this system. This is this was a dock in the Balearic Islands. So they remodeled the passenger's dock because it was deteriorated. So we installed sensors in the pillars that were used for the remodeling of this dock. As you see, it was a installation new construction. We placed sensors on the metallic reinforcement before the concreting stage takes place. Well, you see the sensors are here. These are working electrodes, a reference electrode for potential corrosion measurements. We have also a thermocouple for measuring temperature, etc. In existing structures, there are two approaches. One is this case where the reparation process consists on the construction on overlaid beams. So it's like we install the sensors on these new pseudo structures on the new concrete mass. So the philosophy of installation is just the same. We place sensors in the new concrete. Here you see it to working electrodes on a reference electrode. And the other is a more complex installation when a reparation process takes place, but we cannot access completely or we don't have new rebars placed on the system. We have to generate sensors in situ. That means we have to locate a secondary metallic bar, which doesn't have a heavy structural support. So we make small cuts to isolate one of these rebars, and then we perform the connections, and so we can maintain the original physicochemical environment of the structure, and we perform the measurements on this on-site generated sensor. Okay, which is this velocity. And just to finalize, I will show you how we are providing the access to this information remotely. As I said, the data are generated on a daily basis, so data is uploaded to the server, where a later algorithm makes the process of this data. On the website that Witeklab designed for this application, we can first access to a map where we can geolocalize the assets with basic information. And then once we are inside each of the assets, we can go and click all of the nodes that are installed on this specific system. So the data that is provided here is referred to the Spanish UNE standards. For corrosion rate, our reference standard is UNE 112078, which is for corrosion rate. And for corrosion potential, the Spanish standard is UNE 112083. Okay, just for reference. Now we have extra additional charts that can be accessed to the, well, sorry, I will go one by one. This is we here provide the temperature, the corrosion current, the potential of the corrosion potential of the rebar, and also of the sensors that we installed inside, and then we plot an estimation of the peak loss of this specific area. Okay. In the additional chart, we can see also the temperature again, the potential. We have the capability of providing the corrosion potential of 4 extra electrodes in case of need, if the user wants to install them. We also provide the electrical resistance of the sensors, of the cover between the sensor and the outer layer, and also the estimation of the corrosion rate. Okay. So the additional charts. There are also added capabilities on the website. You can plot some of the parameters versus each other. So sometimes useful information can be extracted from this. You can see seasonal evolution of the parameters compared to temperature. Or sometimes it's very useful to plot the corrosion potential versus the corrosion current. And last thing I wanted to show you, we have a multiple selection of all the sensors on one installation. So for example, you can plot all the sensors you have installed, for example, the corrosion current or corrosion potential. That's it. So from my part, that's it. I think I will let Dr. José Ramón to continue with the most theoretical part of the presentation. José?
Jose, you're trying to share the screen. It's, in my view, it's still very black. Can you hear me? Not very well, but we can hear you say something. Maybe we will later see if it's good enough. Maybe you should start.
I'm trying to share my screen. Okay, can you hear me? Can you see my screen?
Yes, so I can see your screen and I can also hear you. Just go ahead.
Okay, I wasn't sure. Okay, my name is Jose Enrique, and I was working in Corrochip doing my PhD, and now I'm part of the Instituto de Ciencias de la Construcción Roja from the Spanish Construct Research. Okay, let's go with the most technical explanation about the system. Okay, let's start from a conceptual point of view. Corrochip, as Roman Bataller indicated, it's a system designed to form an integrated network of sensors. What does this mean? Well, it's make it possible to monitor the corrosion state simultaneously at different points of a structure, even in inaccessible parts. To do this, in each evaluated zone point, there are a series of sensors with the measurement electrodes embedded in the structure and the electronic components placed externally to facilitate possible maintenance tasks. The different points are managed by a central module in which a microcomputer interrogates the different sensors and automatically transforms the gated raw data in meaningful corrosion parameters to finally provide the monitoring results that Roman has shown us previously. As explained, also the information can be remotely consulted via corresponding web applications. So, and what do we find in each control point? There is the sensor. On the one hand, there is the embedded electrode that make up the sensor, which are connected to a miniaturized potentiostat that is in charge of measuring corrosion that is interrogating the sensor. So the embedded sensor consists of a measuring cell containing 3 electrodes. All of which are embedded in the concrete. The main element is the working electrode, which consists of a section of the reinforcement. Electrochemical polarization techniques applied to this working electrode to determine the corrosion parameters. The electrochemical techniques are based on recording the response of the electrode when an electrical perturbation, either in the form of or potential, is applied to this working electrode. To apply this type of techniques, 2 other electrodes are needed in the cell. On the one hand, this is the counter electrode through which the electrical perturbation is applied to the working electrode, and on the other hand, the reference electrode, with which the potential response of the working electrode is monitored. Okay, so the polarization technique obviously is applied with the potentiostat. Okay, what are the parameters obtained with the sensor? The main one is corrosion rate. This is a parameter of great importance as it expresses the reverse section loss per unit of time, usually in micrometers per year. This is a parameter expressed usually in terms of current, because you can see they are equivalent. So normally we work in terms of current, mean parts per square centimeter. So from the corrosion rate, the section loss of reinforcement for a specific period of time can be determined with that expression. So when determining the corrosion rate, Corrochip corrosion sensor has a particular advantageous operating principle in which 2 modes of operation can be distinguished. On one hand, the connection mode, in which the working electrode remains continuously connected to the reinforcement. In this way, we ensure that it is fully involved in the macrocell corrosion process that may occur in the structure. For example, this phenomenon could occur between the buried zone and the aerial zone of a pile. The aerial zone to higher house demands large quantities of electrons, which are provided by the zone more prone to give them. That's a buried zone, almost in presence of chlorides. According to different studies, this type of process can accelerate the corrosion of anodic zones up to 5 times. So in the connection mode, the macrocell corrosion current between the working electric structure is recorded. And on the other hand, once a day punctually, the working electrode is disconnected temporarily from the structure, and the local corrosion current, the microcurrent, is measured by applying the electrochemical appreciation techniques. Okay, so the actual rate is the sum of both of them, the macro current and the microcurrent. Okay, so as mentioned above, Corrochip sensor uses a new polishing technique to determine the local corrosion rate. This is the potential step voltammetry technique. Is an innovative alternative to traditional methods. On the one hand, there is the TAFEL extrapolation method, in which the corrosion rates obtained by interseeing the linear regions that appear in the polarization curves obtained in response to wide potentiodynamic scans. It is an accurate technique. It has the disadvantage of being very slow and time-consuming, which can lead to high rebar polarizations, which can lead also to irreversible alterations of the region. So the reference technique is the linear resistance method. The advantage is focused on the area close to the corrosion potential, the equilibrium potential. So the polarization applied is small and the measurement is relatively short, a matter of several minutes. In addition to polarization resistance, other parameters such as electrical resistance of concrete are obtained. But the disadvantage is in the calculation of corrosion rate from the RP. We need to assume a value of 26 millivolts of one of the constants of the Stern-Angeli model, which will introduce a significant in results. So the new polarization potential step voltammetry technique used in Corrochip is designed to overcome the disadvantages of these classical techniques while retaining their main advantages. So in the PSV method, it is based on the TAFEL method, and that is current is obtained from the intersection of the TAFEL lines. However, with PSV, each TAFEL line is obtained only through 3 points. In this way, these are obtained much more quickly, and most important, without risk of producing irreversible polarization of rivers. For this purpose, an alternating circuit anodic and cathodic pulses of increasing amplitude are applied. Each point on TAFEL lines is obtained by modeling the system response to that pulses by using a curve fitting with specific equivalent circuit. So the value of the point coordinate corresponds to the Faraday current is passing through the model at the state, whereas the abscissa corresponds to the applied O potential, which is obtained by subtracting the ohmic drop to the applied potential. So corrosion current finally is obtained by intercept of lines. So in addition to the corrosion rate, from the fitted value of the components, we can obtain other interesting parameters such as the double layer capacity related with the amount of rust related at the steel concrete interface, and another interesting parameter, which is the electrical resistance of concrete. Why is the electrical resistance so important? Because it's the parameter we use to obtain another one. This is resistivity of concrete. We only need to multiply the electrical resistance by a cell factor, which we have previously calibrated and put in a specific paper. All the rest done with the method and with the resistivity calibration has been published previously. Okay, here are some of the results obtained in these studies. For example, the validation of the corrosion rate obtained with PSV versus the reference methods, showing small distribution with the TAFEL method and also with the gravimetric method. And also resistivity was validated against reference methods, showing good correlation. So, okay. Therefore, Corrochip sensor, in addition to corrosion rate, provides concrete resistivity. Resistivity is highly dependent on the microstructural properties of concrete, such as pore size and the shape of the pore interconnections. Therefore, the magnitude of this parameter, usually in kiloohms per centimeter, is linked to the ability of the porous network to facilitate the diffusion of aggressive agents, such as chlorides or carbon dioxide. Consequently, resistivity is used to evaluate the reinforcement corrosion risk for the covered concrete quality. These are the corrosion risk categories associated with resistivity value proposed by the RILEM recommendation. Okay. The other parameter we obtain with Corrochip is the corrosion potential, as our reference electrode is included in the measuring cell. Okay, so this is a measurement of the electrical potential of the reinforcement, as its potential becomes more negative when the corrosion process is more active. This is actually a relative measurement, since the potential difference between the reinforcement and the reference electrode is recorded. Again, the corrosion potential is associated with corrosion risk level. Okay, the limits between these levels depends on the type of the reference electrode we are using. This is the criterion given by STM for the copper sulfate electrode. So at the end, both parameters, resistivity and corrosion potential, are qualitative. That is, they will only indicate whether there's corrosion or not in terms of probability. Low probability, high probability, or uncertain level, maybe yes, maybe not. This is like something like rain forecast. We know the probability of rain tomorrow, but we don't know how much it will rain whenever it will rain a lot later. So it's like more or less the same. The advantage of these techniques is that they are quick and relatively easy to apply. And in addition, they support the interpretation of the most important parameter, that is the corrosion rate. As we have already seen, the rate is a quantitative parameter, as it allows us to determine reinforcement section loss. In fact, it's the parameter used in the various service life prediction models some specifically when analyzing the propagation period, that's the period after the reinforcement, the passivation until the end of the service life. For example, the European standard Eurocode 2 proposes a model to estimate the reinforcement retrocession reduction considering a pitting factor, whose value depends on the type of attack. 2 for generalizing corrosion, and between 5 and 10 for pitting corrosion by chlorides. So, in addition, the Convectec inspection guide proposes a model for estimating the crack width generated by the reinforcement corrosion. So we can predict when some specific crack width will be reached. Okay. So it should be noted also that the corrosion rate fluctuates over time due to variations in temperature and humidity associated with additional cycles. Therefore, it is critical to continuously monitor the corrosion rate in order to make the model estimates as accurate as possible. And that is that we made with Corrochip. A continuous real-time monitoring of the three key corrosion parameters. Okay, that's all for my part. And next, our partner from UPB, Dr. Jose Ramon Giso, will show you some real implementation of the Corrochip sensor and some.
Can you see my presentation?
Yes, also we see the screen, yeah.
Okay, perfect. So good morning. My name is Josep Giso and I am PhD architect, and currently I am working as a professor and researcher at the Polytechnic University of Valencia. In this presentation, I will follow the line of my colleagues and I will present the work we have done in the laboratory for the validation of the sensor network Corrochip. Later, I will show you some examples of real implementations and some ideas and future works. First of all, laboratory validation. Often, the approach to sensors embedded in concrete is to introduce isolated elements on which corrosion is measured. However, this is a mistake, as the rebar, and as Jose Enrique commented, in reinforced concrete structures is continuous and interactions occur between different areas due to different exposure conditions. These interactions are called macro-cell currents, and only when this is taken into account together with the micro-cell corrosion, for example, corrosion due to local conditions, can the real corrosion of a rebar to be known. On this basis, the research group in which I am involved designed a sensor that remains electrically connected to the rebars and takes part in the existing macro-cell currents. When we want to measure corrosion, there are two measurement positions. First one for measuring the macrocell current, and the second one to measure the microcell corrosion current using the technique described previously by my colleagues. As it is possible to know the total corrosion of the sensor, which in this case is representative of the closest rebar where the sensor is located. Correct? The validation of this corrosion monitoring method was carried out on specimens manufactured with 5 different concretes. As you can see, they were partially submerged or immersed in seawater. For 1 year, corrosion monitoring was carried out using the methodology described above or described previously. Periodically, macrocell currents were analyzed, and then microcell corrosion analysis was performed. Here you can see the results obtained for some of the test specimens. I'm not going to describe them in detail, but I will leave a link at the end of the presentations to the manuscripts where the results were published and described. In case anyone wants to know more about this study, I will focus on the validation. First, the study was accompanied by a detailed visual inspection, classifying the test specimens according to the type of concrete and damage we found. Okay, as you can see, From this picture, no corrosion was detected on ultra-high performance fiber-reinforced concrete specimens, but large rust stains and even small cracks were detected in ordinary concrete specimens. And then a visual analysis of the rebar was performed as well. The rebars were subjected to a cleaning process which revealed serious corrosion damage. In this case, significant pitting was detected. Validation of this type of study is usually carried out using gravimetric technique. However, the authors of this study also decided to use a very precise scanner to identify even the pits in detail. As you can see, the detailed analysis of the pits is incredible. This analysis and the gravimetric study were compared with the results obtained by estimations using the Corrochip monitoring data. As can be seen from the graph, the deviation is minimal, close to 5%, the black line. On the other hand, when using methods that not consider macrocell currents, the deviation committed is more than 90%, represented by the continuous red line. As I said earlier, this work is accessible and can be studied in more detail, but in summary, this study proved the accuracy and reliability of the monitoring system and the measurement method. We are currently working on improving this monitoring system. We are analyzing scaled elements such as columns, slabs, beams, and even existing structures and repairs. In most cases, these studies have already been published. However, I will go a little further, and in the second part of the presentation, I will show you the first prototype of a Corrochip monitoring system and some examples. First of all, I would like to present the implementation methodology. Each sensor is located close to the rebars thanks to 3D printed parts, and they can be placed in different geometries, as you can see. Each sensor is connected to the small microprocessors my colleagues have presented previously, and they take measurements every day and they store the data. As you can see, they are very small elements that can be placed anywhere on the structure. Later, the measurements are sent via wireless to a data server, which allows the results to be viewed in real time. Depending on the number of sensors implemented, you will have more control points in your structures. This is the first prototype where Corrochip was implemented. It is located in the gardens of the university campus, and as you can see, the sensors were previously placed. And as a novelty, a solar panel was installed so that the microprocessors can work autonomously. In this way, the monitoring system can be implemented even in structures where there is no power supply. Here are a few examples of what I mean. The first structure where the INSCOM system or Corrochip system was implemented was this raft. It is an offshore structure for shellfish farming. As you can see, they are large structures that are located on the seawater. And they used to be made of wood, but for durability reasons, they are now made of concrete. The location means there is no power supply, so solar panels and an auxiliary battery have allowed daily corrosion monitoring for over 3 years. These structures are exposed to very aggressive conditions, and it will be common for corrosion problems to appear in a very short time. However, this work has been published, and thanks to the fact that the rafts are made of ultra-high performance fiber-reinforced concrete, corrosion is practically negligible, as you can see. Another example is this one. Is a newly built platform with the purpose of housing and public space and leisure area on the sea. In this case, the Corrochip monitoring system has also been implemented, although the results have not been yet published. The third case I want to show you is this series of ridges in central Spain. In this case, the problem is not chlorides from the sea, but the ising salts from the roads. Unlike the previous example, this is an existing structure, more than 20 years old, where the Corrochip system has been implemented to improve corrosion assessment and evaluation. This demonstrates the many possibilities offered by Corrochip, new structures and existing structures in any exposure condition. This is the last example. Sorry for the noise. It is a prototype developed at the university in collaboration with other European universities. This structure represents an offshore wind turbine float. It was designed using ultra-high performance fiber-reinforced concrete, and Corrochip was implemented to validate the material performance under service conditions. Corrosion was monitored over a period of 2 years, and in addition, visual inspections and core samples were analyzed. As you can see, and as will be published soon, Corrochip has not only allowed corrosion to be monitored, but also validated this type of concrete, which is something that many companies are also requesting. Finally, I would like to present the future works and ideas that we are currently trying to implement. To do this, I will show you a project that was designed as a proposal to improve the city of Valencia and that has won several awards. This is a proposal to implement sensors in urban areas, for example, in small housing, demonstrating that it is possible to monitor the corrosion condition in reinforced concrete structures in real time, even with a small mobile device. This can also be applied to large infrastructures such as stadiums or even areas like this one. This is the university campus. This campus is less than 500 meters from the sea, and corrosion is a common damage in these buildings. This has caused many problems, and the proposal is to implement Corrochip for early detection. The aim is to have an application with the university that will allow us to receive alerts of corrosion problems in any building, or even analyze the corrosion condition using virtual reality tools. In this way, resources in cities could be optimized. By simply using Corrochip, late detection problems with visual inspections could be avoided and large amounts of money could be saved. And last but not least, how can INSCOM be implemented or Corrochip be implemented in your cities? Let me give you 2 examples. I lived for a year in Trondheim before finishing my bachelor's degree in architecture as an exchange student, and there I fell in love with this building, Dora 1. During my stay, some small exhibitions or temporary activities were arranged there. Currently, I have noticed there are more activities and there are many people coming to the building every week. The implementation of Corrochip will be useful to monitor corrosion and make corrosion assessment of this structure easier, reliable, and accurate. This will reduce maintenance and repair costs. And on another scale, this could be another example, a large engineering structure. As you can see, Corrochip will allow real-time corrosion monitoring of the structure, and it will be possible to know the status in detail and only using a mobile device with internet connection. I hope you have found this presentation helpful. And on this slide, I have let you some of the most recent publications, just in case you want to know some more details. Thank you for your attention.
Thank you, Josep.
You're
So
welcome.
I think I would like to stop the recording now, Ignacy.
Yes, that's okay.
Okay.